Okay, we are now going to seemingly change complete gears and talk about something that's going to look like at first has absolutely nothing to do with what we're doing. This is where I want to do the Monty Python, and now for something completely different, because that's about already what's going to happen here. But it does have something to pertain, because we're going to talk about not only logic circuits, but how to start optimizing them. And this is something that Verilog can do somewhat for us, the Verilog compiler or synthesizer. But we are computer scientists, and we need to at least understand what it is doing for us so we can utilize the tool better. And so we're going to learn how it works and be able to do some of the circuit analysis ourselves. And also that'll help us understand the limitations of the software that is trying to optimize the circuits for us. But before we can get to that, we need to start talking about Boolean logic. Now, unfortunately, how many of y'all are either in or taking discrete math? Less than half the course.
Different.
Yeah.
Oh, not completely different. It's just worded.
So you learn everything I'm about ready to show. You learn probably 80 to 90% of it in discrete math, except for the K-maps and the sum of min terms and whatnot. But we'll get to that. So while this is a review, obviously other parts of this would be a lot easier. But I have to assume you haven't taken discrete math. So they do an overview. Part 1 is the equations, part 2 is the optimization, and we are not doing part 3 because we don't have time for that. But only 1 and 2 I think are the most important. Okay, so binary logic. Binary values take one of two forms. Hey, that's great. Logical operators, of course, operate on those. Those are and, or, and not. These should look very familiar. Logic gates implement the functions, and a Boolean algebra, which is what we're going to start introducing now, is a mathematical system for specifying and working with these. So we study the Boolean algebra because it's a foundation of our digital systems, at least the theoretical foundation. So we have true, false, on, off, yes, no, or 1, 0. These are all interchangeable, and I've been using them interchangeably as well. Hopefully this is intuitive. 1 is on or true or yes, and 0 is of course false, it's off, no, or low voltage. I've also been saying high voltage and low voltage as well. The slides are going to try and stick to 1 and 0, and you can have variables inside our algebra because it's an algebra. 3 basic operations are and, or, not. Hey, look, we've already implemented that in a circuit, which is great. And is used by a dot. What does she use in discrete math for and?
It's like a caret.
Oh, the caret.
And then the other one's a down caret.
Oh wow. Yeah, you're just.
That's really confusing.
You're gonna have to live with that.
Yeah.
Because I'm not gonna change that. If
you can't change. No, you can't change math notation. That's just math notation.
Well, this is math notation too.
I know, but
oh well. So and is a dot. So it's not multiply, it's and. Or is a plus. So it's or, it's not plus. A not is an overbar on top of it. So you may have seen the circuit where you had a B and then that bar over it. That means not B. You can also put a quote after it to make it a not, and I think I went over that in our last slides. Or you can put a tilde before the variable to be not as well.
That's what they use, the little tilde.
The little tilde. These are all equivalent notation.
Yeah.
So y equals a and b, that's how that's read. The next one is z equals x or y. And the third one is x equals not a. By convention, you put the not in front of the variable. So even if there's a little asterisk 1 right here, you can still say not a. So the bottom one, 1 plus 1 is true, but 1 or 1 is 1. All right, which is also true. All right. I know, guys, it's going to be a little weird. So let's see. So you have and 0 and 0, 0, 0 and 1 is 1, 1 and 0, 0. All right. And then you have or 1, or I'm sorry, 0, 0 is 0, 0 or 1 is 1, etc. And then of course you have not. Not 0 is 1 and not 1 is 0. How are we doing? All right. Truth tables. Hopefully I have written some of these out. And here's some more examples. So I just want to talk real quick about switches. So logic 1, the switch is closed, which means that it's connecting. So these are an example of the switch being open. Switch being closed is that goes down and touches the end, which makes it closed, which makes it a 1. 1, the light is on. 0, the light is off. And then not. You can implement these with switches. That's what a transistor is. A transistor is an electronic switch. And you can do more complicated circuits if you want to with switches, but we've already talked a little bit about that. And used for CMOS gate circuits. CMOS is a standard manufacturing technique in order to etch transistors electronically on silicon using the doping that we talked about earlier. All right, they like the history. So in earliest computers, they had a bunch of relays running around that would switch open and on based on your input. Later, they came up with vacuum tubes, which were a great improvement. And then today, we use transistors. Just notice that these are all serve the same function, just transistors are smaller, consume less power, and are much, much faster. So here's our logic gates. Again, the round bullet is an AND, the pointy bullet with a curved bottom is an OR, and the triangle with the circle is a NOT. We talked a little bit about gate delay, but here again in the picture. We showed a picture beforehand, but the gate delay is how long it takes for the input to affect the output. So gate TG is the gate delay here, TG might be here as well. Hopefully it's always the same. And so it may be some value like 0.3 nanoseconds in order to get through the circuit. Hey, logic diagrams and expressions. So if you wish to express a circuit, you could write out the truth table like this. It has inputs x, y, z, and its outputs are x or not y and z. And then those are the outputs. You could also write the equation, or you can draw the diagram. Does that diagram look familiar? They all describe the same function. The only one that's unique is the truth table. Because you've done equations where you get multiple equations evaluate to the same output. Hopefully you can realize that your diagram may be different depending on how you write it. But the truth table is going to remain the same, because the truth table says is the brute force method. Here are the inputs, that's what the output is. For these inputs, that's the output. For these inputs, that's the output. And then brute force, aka iterates through every possible input to tell you what the output is. The truth table is unique, the rest are not. This has some consequences, because that means that there may be a more optimal circuit to etch into your silicon than what you're currently looking at. Or there may not be. We need to come up with a way to try and figure it out, or at least help. All right, Boolean algebra. I'm not going to ask you to memorize these. The top one should be pretty explanatory. Anything ORing or 0 is going to be whatever that was to begin with. Anything and 1 will be what it is to begin with. Anything or 1 is always 1, and anything and 0 is 0. So x or x is x, x and x is x, of course. X or not x has to be 1, because one of these has to be 0. X and not x has to be 0, because one of them has to be 0, and looks for 0. And number 9 is a very nice result in Boolean algebra. Not x is x. So we're good. There's no like extra third value that pops up. That's only if you messed up your circuit. In the algebra, not x is going to be x. There are the commutative properties. Basically, you can flip the order, it doesn't matter. You can do the associative as well, where the parentheses doesn't matter. Let's see. Oh, distribute out the values. And then De Morgan's law is the one that, if you haven't taken discrete math, is going to be new. Let me read it. If you're knotting the entire expression x or y, that is equal to not x and not y. But you have to be knotting the entire expression. Similarly, if you're knotting the entire expression x and y, that becomes not x or not y. That's De Morgan's law. And anyone take philosophy? They usually actually do this. Yeah, this will be in your philosophy logic course. All right. So it's not too important, but what are some common Boolean algebras with more than 2 elements? Well, you can have your algebra of sets. You're going to go through set theory. In-bit binary vectors as well, so maybe you want to have 32-bit numbers running around. But if B, which is your universe of values, or your language, depending on which math professor you have, it's then called a switching algebra, and it's one we use most often, or is really what we use in computers or circuits. Order, parentheses, not, and, or. So, parentheses have precedence over everything else, not has precedence over and or, and has precedence over or. This is why the syntax of using the dot for and was chosen, because we all learned that multiplication has precedence over addition. So the precedence, by using this type of syntax, we get the precedence order down, basically for free, because we've all been taught this precedence growing up. Unfortunately, we have to remember what a plus means now, but you got to choose one or the other, or you can do the caret method, but then you got to remember your precedence rules. No one's going to win here. You got to choose something. All right. Hey, look at that. The slide is a little funny. All right. Proofs. If you haven't taken discrete math, you're not used to these proofs, but we want to prove something, namely that A or A and B is always A. This is called the absorption theorem. How do we prove this? Well, we start with A or A and B, and we're going to start applying rules that we've already did previously in our previous slides to here until we get to the value A. And since we're going to be using equals, that means we can go both directions. aka we can go from A or A and B, aka from here down to A, and we can go from A up here as well by following the rules. And so this is our proof. So the first thing we did is we had A and we AND it with 1, because A is also equal to A and 1. All right. Then we took that 1 and we transformed it to 1 or B, because 1 or anything is always 1, so that's still legitimate. Then we're going to, oh, I'm sorry, that's not what we did. I lied. We're going to remove the A. Whew, that was bad. So we distribute out the A to here, and so you have A, and inside you have 1 or B. Now I was skipping ahead because 1 or B is always 1. So now you have A and 1, but we also know that anything and 1 is the thing to begin with ourselves. So there is a proof of the absorption theorem that A or A and B equals A. Now, discrete math is where you're going to go more into the theory and how you prove most of this. But the point is, if you had, looking at this diagram, and that diagram, it may not be completely obvious to you what's going on, because you might have A, that's not a good shot. You might have A, and that's going into an OR. That needs to be pointy. And then you might have B down here, going with A fanning out, going to an and let's see, and then that goes into here. And then you have your output. When you first look at that, it may not be apparent to you that that's just A. By using this theorem, we just proven that it has to be A, which is why this is important. All right. Oh, any guesses on what we do here? Well, that's a pretty big hint, because whenever they take 1 and they put it to A or not A, which has to be 1, obviously they want you to distribute out the BC. So that's 1. Okay. Now what do we do? Well, we have a not AC here and a not AC there, and then we have 2 ABs right here. Let's first pull out the AB. Last term, so this is going to be. Did I do that right? Right. Okay, so it's 1 or C is always 1, so we know that this is AB. 1 or B is always 1, so we know this is A, not C. Is that what we wanted to prove? Yes. All right. So a lot of times I'll have a student ask, how do we know what to use? You got to figure it out. There's not much else I can tell you. But this is not discrete math, so we're not going to be doing a lot of this. We'll be doing some, though. I will require a sum just to get you to practice it for homework, but that's going to be the end of it. Other theorems, and you can study these if you want to, and these may be helpful for your homework, but we're not going to go through them too much today. We're not, wow, proof of simplification. I'm not going to do this right now. Or of De Morgan's law, because those are covered in discrete math. You may just assume that they work. But for here, this is pretty important. Let's see what we got here. Boolean function evaluation. Let's see. Oh, they are not being helpful here, or kind. Oh. So you have your different inputs and you have your different functions. The point here is you could fill out the the truth table to actually brute force what the answer needs to be. Excuse me. So let's see. How about the all zeros? What's F3? No. They're all zeros. What's the first term? Take a breath, Barry. If you're nodding all the zeros, and then you're anding the not of zeros, what does it have to be? 0. Well, not 0 is 1, not 0 is 1, not 0 is 1, 1 and 1 and 1, 1. And then you're ORing other stuff, so the answer has to be 1. So really, if you look at this, what it's saying is that F3 is 1 if x, y, z are 0, or if x is 0, y is 0, and z is 0, or if at any point x is 0 and y is 1. So this has to be 1. And that has to be 1, because that's the don't care on z. And what was the other one? So when we have 0 for x and 1, 1, so it'd be true here as well. Oh, I'm sorry, not these two. Oh, my apologies. Oh, that was bad. These two are true. So you can fill out the truth table. You do okay, Brian?
No.
No? All right, I'll try and
I'm here.
do some of the review. All right. Now, what's going on here? Well, okay, sure. It may look bad, but it's not. So, yeah. So the point here is we have a bunch of ands and stuff running around up here. One way to optimize a circuit is to reduce the number of terms being used, which is nice in that it reduces the number of gates you need, because that means you have fewer gate inputs that you have to evaluate. So one thing is called expression simplification, to contain the smallest number of literals, complement and uncomplement. Now, so we start off with some really long expression, and then they just copy pasta it. Yeah, they just put that guy right there. This one was over there, and he was right there. Okay, great. And they did that so that they could, let's see, take the CD out of here and here? No, oh no, they just put parentheses around it. D or that, and then over here is what it looks like they combined it. How did they combine that? Oh, they can take the A knot out, which is nice. And then you have CD or BD. Oh, and since you have the knots on the two end, it just goes down to BD. That's one of our previous theorems. And so down here, they took the AC over here. What did they do here? We are missing some steps here. Otherwise, it's not going to make much sense. Wow. That's the same, that's the same. So they took these three terms and moved it to A naught C. Ooh, so how did they figure that one out? Well, they probably multiplied it out. Oh, and then you have CD here, which you can get rid of, and then you have BD. Yeah, there's a lot of writing in here that they totally skipped, that they should have told you. But there is a means in order to simplify it. In this case, it comes down to 5 literals, as opposed to how many literals are up top. A literal is an actual input. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, down to 1, 2, 3, 4, 5, which is a lot better, because now you have fewer gates. All right. Although I'll tell you right now, fewer gates does not mean the circuit is faster. And we'll get to that in a bit. All right, 10:45, I think we're going to finish now, because we're running low. Yeah, we're doing good.